Hello, this is Math 2270 coming to you from the College of DuPage during the summer of 2020, and this is a continuation of the linear and nonlinear modeling. This is the problem I set you about doing. Perhaps you finished it, I hope so, but if not, you know what to do. Let's see how you do. I put the problem up here so we can refer to it if we need to. Now remember that the concentration is the amount of salt in the tank at any time t divided by the volume of water in the tank at any time t. So you see the rate of change is going to be the input, which is a rate of 9 gallons per hour. Well, you can see that up there. And it goes out at 6 gallons per hour. And the concentration of the incoming material varies as a function of t, and you can see that's what we have up here. Yeah, it's over here. That's the pounds per gallon. And again, that's a concentration because it's pounds per gallon. And so it is coming in, so input minus output. Now, the concentration of the output is going to be Q of t, how much ever is in there, and we're assuming it is fully mixed. But then what happens is we're inputting 9 and outputting 6, so every hour we gain 3, and we started with 600. So Q of t is how much salt is in here. We started with 600, but we're gaining 3 gallons every hour from this process. So this is the input minus the output. And since you initially had 5 pounds in the tank, this is what you your initial condition, and this of course can simplify to this. You should check these calculations because on an assessment you would be doing these calculations. So we'll go to the next page to solve this. Now you see you can reorganize that one, and that in fact is linear because there's Q prime, there's Q of t, and then you have this function of t, and this is the right hand side. So this is a linear first order differential equation which we can solve using an integrating factor. So we find that the integrating factor is in fact this. So we multiply all the way through by this integrating factor, and you can check that, but this is a correct integrating factor, and then we integrate both sides. And so this integral is easy because it's just the derivative. It's going to give you this. This integral is going to be, in some instances, a little more complicated because you're going to be integrating by parts 2 or 3 times there, maybe 2 times, actually maybe 3 times. But anyway, you'll be integrating by parts some, and there's a lot of algebra involved, and I'm putting my constant over here because I want to solve for Q of t, so having the constant on the other side is useful. And then I'm going to divide all the way through by the coefficient of Q of t because that's what I want to solve for, and I get this expression. And now we're ready to use my initial condition. My initial condition here I substitute in and I get C is this number. So the overall equation, the amount of salt in the tank at any time t, is given by that expression with the new C substituted in. Now, the tank will overflow at t equal 300 hours. You can get that from the parameters given early because you're always gaining 3 per hour. You started at 600, so you overflow at 1500. So what you can do is you will take 300, plug it into that equation, do the calculation, and that's how much salt is in when the tank overflows. Here's another problem. A 1,000-gallon holding tank catches runoff from some chemical process initially, has 800 gallons of water with 2 ounces of pollutant in it, dissolved in it. This must be bad stuff, 2 ounces and 800 gallons. Anyway, polluted water flows into the tank at a rate of 3 gallons per hour and contains 5 ounces per gallon of pollutant in it. There's some nasty stuff being sucked off here. A well-mixed solution leaves the tank at 3 gallons per hour as well. When the amount of pollution in the holding tank reaches 500 ounces, the inflow of polluted water is cut off and fresh water will enter the tank at a decreased rate of 2 gallons per hour, while the outflow is increased to 4 gallons per hour. They're basically flushing the tank. Determine the amount of pollution in the tank at any time t. You know what to do. And in 13.2, we'll see how you did.